Hello and welcome to the final video of this first part of the course. We're going to end by considering situations where an isolated singularity lies on the integration contour. The corresponding real integral is divergent, but we can use a limit to define something called the principal value of an integral. This lets you assign a finite value to such integrals under certain conditions. As a quick recap of what we looked at last time, we saw how to compute integrals of multivalued functions, and that involves using a branch cut to make it single valued, and then a keyhole contour to integrate along. In particular, we also noticed that care must be taken for contributions to such an integral on either side of the branch cut, and that's due to how we assign principal values to angles in such a setup. The intended learning outcomes for this video are given here. You should be able to understand Koshi's principal value integral as the limit of a sum of convergent integrals. And you should also be able to determine the contribution to a contour integral from detours around isolated singularities that lie on the real axis. As usual, there are some questions in the associated problem sheet for you to test your understanding. And now let's start the final video of this part of the course.
In this final video, we're going to talk about principal value integrals. So far, we've seen how Cauchy's theorem can be used to calculate contour integrals where there are no enclosed singularities. And in topic 7, we derived the residue theorem that allows us to compute contour integrals where the contour encloses isolated singularities. Also, in the previous video, we saw how to avoid branch points for our contours because they are not isolated singularities. The next question to ask is, what about if there are isolated singularities lying directly on our contour of integration? That's the question we're going to talk about in this video. Okay, so this is the question that we want to dig into in this video. So let's consider the setup of this problem. Let's suppose that we wish to calculate some real integral, which is given by the integral from -infinity to infinity of a real function, but the analytically continued function that we talked about at the start of topic 8, the analytically continued function has a simple pole that lies on the real axis. Let's call that point x0. You'll recall that a simple pole means that -1 is the most negative power in the Laurent series. Okay, well, as usual, we're going to think about a contour integral. So consider the integral around a closed contour C of our analytically continued complex function f of z. I'm going to draw a picture of the setup and we'll figure out what the contour C is going to look like. We have real, imaginary. We have a simple pole here at x0. And as in previous videos, because we want to calculate a real integral whose limits go from -infinity to infinity, we're going to have part of our contour C lying along the real axis, with a crucial difference this time. We're going to add a path to go round this pole on the real axis. And as before, we're going to close this contour with a semicircular arc. I'll also label, we have minus r and r that we're going to be taking to infinity. I'll also label the different paths making up this closed contour and add their directions. So that's C1, C2, C3, and C4. Additionally, I'm going to suppose that our function f of z has some other poles that I'm going to represent as a set of points, zk. The last thing I'm going to label here is that the radius of this detour, this circular detour, is delta. Okay, so we can now write out our contour integral in terms of the contributions along each path. So the contribution C1, reading off from our picture, C1 lies on the real axis, so z equals x, and we have the lower limit is minus r, and the upper limit is x naught minus delta, the radius of that small detour. This is going to be f of x dx. Next, the contribution along C2, which I'm going to label with this arrow going clockwise, and this is an integral of f of z dz. The contribution along C3 is again along the real axis. The lower limit is x naught plus delta. The upper limit is r. This is going to be f of x dx. And the last contribution is the contribution from the large semicircular arc at the top, traversed anti-clockwise. That's C4, and that's f of z dz. From the residue theorem, we know that this contour integral is going to be given by 2 pi I times the sum of the residues at the enclosed singularities that we've labelled as the points zk. Okay, how do we tackle these contributions? First of all, let's look at the detour integral along C2. Alright, consider what we've called the detour integral about x naught. I'll also note that we assume, as I mentioned earlier, that x naught is a simple pole. This means that we're allowed to write the complex function f of z as some other analytic complex function divided by z minus x naught. So this is where g is analytic. The pole comes from the singularity given by the denominator here. You'll recall that we did this kind of decomposition in the third video of topic 8 when looking at how to compute residues. Okay, let's now look at the limit as delta tends to 0, so shrinking the radius of that detour, of the contribution along C2. Here I'm going to substitute in f of z in terms of g of z. So this gives g of z over z minus x naught dz. I'm now going to perform a substitution. I'm going to let z equal x naught plus delta e to the I theta, which is fine because this is exactly how you would describe the points along the semicircular detour C2. The differential that we need here is I delta e to the I theta d theta. What does this do to our expression above? This now gives us the limit as delta tends to 0, and theta is now our integration variable. And if you look at the picture at the top, the contour C2 has an angle starting at pi and ending at 0. So our integration limits are from pi to 0 of g of z, which is g of x naught plus delta e to the I theta, divided by z minus x naught, that's delta e to the I theta, and then times the differential. Immediately you'll see that the factors of delta e to the I theta cancel. And you'll also note that as delta tends to 0, g of x naught plus delta e to the I theta, that's going to tend to g of x naught. So we can take that out of the front of the integral and obtain I g of x naught and then the integral from pi to 0 just of d theta. And that's easy to do. We end up with minus I pi g of x naught. This is our contribution along C2, and this is half the contribution you would get if you actually enclosed the singularity and used the residue theorem. With a negative sign, because looking at the diagram, the contour is traversed clockwise. You can see easily that g of x naught is the residue at the point x naught from our expression here. This effectively gives us the Lorentz series of f of z, and you can read off the coefficient associated with the power minus 1. By the way, you might recognize the calculation we've done at the bottom of the page. We actually already calculated this in the third question of problem sheet 7, but we considered arbitrary limits θ2 and θ1 instead of 0 and pi as here. Looking at the top of the page, let's now consider what happens when we take the following limit. We take the limit as delta, the radius of the detour, goes to 0, and r goes to infinity of our contour integral. Now we can write down what happens to the different contributions from the top of the page. The first contribution along C1 is going to give us the limit as delta tends to 0 of the integral from minus infinity to x naught minus delta. The contribution along C2 is what we've just calculated, so this is minus I pi g of x naught. Next, the contribution along C3 is the limit as delta tends to 0, the integral from x naught plus delta to infinity. And the last term is the contribution from C4. For this last term, I'm now going to assume, as usual, that this contribution vanishes as r tends to infinity. And that will be either by Jordan's lemma or the fact that the integrand vanishes faster than 1 over z. Now in this expression we have two terms that still contain a limit as delta tends to 0. And these terms define something called Cauchy's principal value integral that I'm going to write down below. I'm now going to define something called Cauchy's principal value integral. I'll explain what it is in a moment, but first of all I'll write it down. It's denoted by a capital P, the integral from minus infinity to infinity of f of x dx. This is defined as the limit, as delta tends to 0, of the terms in the line above which have delta in their integration limits. This is our definition of something called Cauchy's principal value integral, and I'll put this in a red box. Okay, what does Cauchy's principal value integral mean? Well, the principal value integral is a number, and it's a number that we can assign to an integral despite the integral diverging. Importantly, in this definition, the point x0 is approached at the same rate from both directions, and you can see that by the fact that the integration limits have delta instead of something like 2 delta. It turns out that different rates of approach can actually change the value of an integral like this. You can check this for yourselves in Arfken, Weber and Harris. The fact that different rates of approach means the value of the integral can change is because the integral we're interested in, from minus infinity to infinity of f of x, is not convergent, and therefore the limit is not unique. How you approach the point x0 matters. Our definition of the principal value here gives a method of assigning a value despite this divergence. Of course, if the infinite integral converges, so does the principal value, and they'll be equal. I'll write down a couple of these points below. So the integral that we want does not converge, and the limit as x0 is approached is not unique. In particular, it can depend on rate or approaching x0. The Koshy principal value is a way of assigning a value to such an integral. As an aside, I'll give some brief justification of why in our definition here we've assumed that x0 is approached at the same rate from both sides. So this is an aside. Some justification for equal rate of approach. And this is not rigorous, but it's to give you a flavour of what's going on. Consider f of x is 1 over x, which we know blows up at x equals 0. I'll draw a picture of this function. We have x, and it looks something like this. Let's label the point where it blows up as x0, which we know equals 0. And let's consider integrating this function from minus a up to a. So we're interested in finding this area. So look at the integral from minus a to a of f of x dx. Well, you'll note that the integrand is odd about x0. Because the integrand is odd, in some ways by looking at the picture, we can think that the part blowing up on the left-hand side of the y-axis will in some way cancel the part blowing up on the right-hand side. This is not rigorous, but just to give you an idea of what's going on, I'll write that the diverging contributions either side of x0, in some sense they cancel. And this motivates us to find the principal value of this integral to be 0. If you didn't have equal rates of approach, this principal value would not evaluate to 0. And there's more information in Arfken, Weber and Harris. So this was an aside. Okay, looking back at what we had earlier, we had shown that our contour integral over here, we took the limit as delta tends to 0 and r tends to infinity of our contour integral. And on the right hand side we now have the principal value of our integral minus I pi times g of x0. I'll write that down below. We now have that the limit as delta tends to 0 and r tends to infinity of this guy is the principal value of the real integral that would normally diverge minus I pi times g of x naught. And from the residue theorem, we know that this integral is given by 2 pi I times the sum of the residues. Tidying this up, we therefore have that our principal value integral is given by 2 pi I, the sum of these residues, plus this term. And we're done. A quick note that this was for an integration contour that looked like this, where the pole was not enclosed by the integration contour. And these were the orientations. It turns out that you recover the same expression that I've underlined in red here if you use a different integration contour. You recover the same expression if instead you were to use this contour. Where now this pole lying on the real axis is enclosed by our contour. This is straightforward to see, because now the detour integral, that's traversed in the anti-clockwise sense. So the contribution you're going to get is I pi is now plus I pi g of x naught. If you repeat the same analysis, the limit as delta tends to 0, r tends to infinity, the integral along this new contour c primed of f of z dz. As before, we'll have the principal value of the integral. We'll now have plus I pi g of x naught from the detour, and this is going to be, by the residue theorem, 2 pi I times the sum of the residues at the enclosed poles, which now also includes the residue at the pole that lies on the real axis. This here is the residue of f at x naught, and by putting this term onto the right hand side, you recover the same result that we had underlined in red. That concludes our discussion about principal value integrals, and in fact that's the end of the whole part of this part of the course. That's the end of our discussion about principal value integrals. As a recap of topic 9 and also looking back a bit at topic 8, we've been using all of the tricks we've learnt to find creative ways to tackle hard integrals. In the previous video of topic 9, we used branch cuts, the residue theorem, and vanishing arc contributions to figure out how to compute a difficult real integral. In this video, we saw that defining Cauchy's principal value for an integral allows us to assign a value to a real integral even though it diverges. As always, you'll get practice on what we've covered in the associated problem sheet. This video marks the end of the first part of Methods of Theoretical Physics that I've been teaching. So thanks very much for listening, and I do hope you've enjoyed it.